Okay, so Draft Science has responded to my Newton's cradle experiment analysis video, and he wanted to double check the velocities by measuring the displacements of the balls with a horizontal ruler. Now, this is how I initially did it in my previous Newton's cradle analysis video, and then he pointed out that this was a bad idea to measure the displacement with a horizontal ruler, and that instead I should measure the arc because the balls follow a curved line, a curved pathway. The trajectory of the balls is curved, obviously. So let me just show you that argument of in a previous video of him.
Right here. And you can see it's never flat. Okay, look at it. As much as we'd like it to be flat, it's not flat. The object doesn't move like a ruler. Okay, the object's moving up as it moves out. So its real distance is this curved line. It's traveling a curved line. It's not traveling a straight line.
So this was in response to me measuring the displacement of the balls with a horizontal ruler. But now that I've done this, I've actually measured the curved line. I've measured the arc and measured the angle and calculated the distance, the length of the arc. Now he wanted to double check this by measuring it with a horizontal ruler. So I find this kind of hypocritical. Now, in fact, I don't have a problem with measuring it horizontally, but he made a problem out of it. And so now that I've done this, I've measured the curve, suddenly it seems that it would be better. He thinks it's a better idea to measure it horizontally. So I just find this in itself rather hypocritical. But okay, if we're going to do this way, I actually think this is more accurate because theoretically, yes, the heavier ball should travel with a smaller velocity, and it is true that when we are going to measure it horizontally, that the distance between the point of collision and the smaller mass is going to be longer than the distance between the point of collision and the heavier mass. So after a certain amount of frames. So of course I wanted to verify this for myself, and now we're going to do it this way again, measuring it horizontally. So first, we want to know what is the exact point of the collision. So here they touch, and then one frame later they start to reflect. So it's right over here. So let's take a print screen, put that on paint. Right, and now let's draw the line, the point of collision, which is right here. Okay, now we also want to put a ruler in there. So let's go. This is going to be my ruler. Take a print screen. So I'm going to show you everything I will do just to make sure that you can follow along on how I do everything. So there can be no discussion, no cheating. There we go. So this is going to take a while. Going to be a rather long video again. So this is going to be the ruler. Now I'm going to, let's see. I'm going to put the zero line on this edge. So I have this cardboard box, this little box, and I'm going to put the zero line right on this edge as a reference line. Right, so this edge. Okay, this is going to be my reference line, the zero line. Okay, so the center, the point of collision is over here. It's going to be 2.5678. It looks like 2.78 or 2.79. All right, so then we're gonna take a look. 10 frames later. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's take a print screen. a print screen. Put that over here. Put the ruler over here. Again, the same place, the edge of the card, the little cardboard box, the zero line over here. Okay, so 2.78 right here, right just at the left from the 2.8 mark. That's the center of mass. So 2.8 is over here, so right over here. Okay. So now we're gonna pick the inside of the ball, not the outer side, but the inside. So clearly, the edge of the 2-mass ball is over here, of the heavy ball is over here, and this one seems to be over here. Okay, so now we're gonna have to calculate the displacement. So we have 2 points for the point of collision, 2 points, let's say 2.7978, 2.78 centimeters. Point of collision equals 2.79 centimeters, and then 10 frames later, so I'm gonna have to do delta time over delta distance over delta time. So what's the difference in distance? So let's see. So they both start at 2.79. After 10 frames, the small ball has traveled to 2.3. It looks like 2.35 or 34. 2.34, I would say. So, which is going to be 2.79 minus 2.34. This is going to be our delta distance. I'm going to have to divide this by the change in time, which is, so we start at 110 and then it's 143. So 0.33 0.33 seconds. Or V1 prime. This is the reflection part. Oh, I also have to do the initial momentum of V1. Oh, it's going to take a long while. Okay, so then the heavy mass, 3.2, exactly 3.2. Okay, so 3.2 minus 2.79, right, divided by 0.33. Which is V2. All right, so oh, now I'm gonna have to let's see, so 2.79, 2.34, right? Divided by 0.33, 1.3636, 1.36, so equals 1.36 meters per second. And then V2, 3.2 minus 2.79, right? Divided by 0.33, 1.24. So it's going slower. Now, yeah, I have to do the incoming speed of mass 1, because we have to do all the measurements. If we're gonna use the horizontal ruler, we're gonna have to apply this to every. We're gonna also have to apply this right before collision, the incoming speed. So this is the point of collision. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is to calculate the incoming speed. Put that over here. Okay, so put the ruler on there. Right over here, put the 0 mark over here. Yep. Now let's see. So 2.78 was the point of collision. Right here. This is 10 frames before the collision. So the edge of the ball is over here. So it looks like 1.9. 1.9. So 2.79. This is V1. Put it over here. V1 equals 2.79, which is the point of collision, minus 1.9, 10 frames before collision, right? Divided by 0.33. The change, the difference in time, 1.9. All right. This is the initial velocity, 2.69. V1 equals 2.69 meters per second. All right, now we can calculate the momentum. So for V1, P1 is the same, 2.69 kilograms meters per second. P1 prime is going to be the same, which is 1.36 meters per second. All right, and then for P2 we have to do 1.24 times 3.36. So 1.24 times 3.36, 4.16. So, right. 4.16 kilograms meters per second. Yeah. Okay. So now, oh, it's not P3, but P2. Okay. So now, if we're going to subtract 4.16 minus 1.36, P2 minus P1 equals 4.16 minus 1.36. Yeah. 2.8. And it should have been 2.69. So we have an increase, a small increase. This is for conventional signs. All right, now for draft signs, we have to add both. We have to add them together because they always are positive. They always have a positive value. So it should have been, okay, so the initial momentum is 2.69. Conventional signs, okay, they subtract these momentums because they go in opposite direction, and that equals 2.8. For draft signs, we're going to add these together. So 4.16 plus 1.36 equals 5.52. Right. Now we're going to calculate the error percentage. Now, calculating that. So it should have been 2.69, but we got 2.8 for conventional signs, which is an increase of 4.089%. So we got plus 4.089%. For draft signs, it should have been 2.69, but we got 5.52. which is an increase of 105.20%. All right, so there we go. I have I've showed you how I've done it step by step. Okay, so now if I've done something wrong, please show it to me. All right, I think I've tried my best to draw the lines as accurately as possible, to find the point of collision as accurate as possible. All right, and to find the edges of the ball. Right, I took the inside of the ball, not the outside of the balls, although that doesn't really matter to me, according to me, I think, but okay. So if I made a mistake, which I think I didn't really, please show it to me. But once again, the error percentages are pretty significant. They are significantly large for draft science model and significantly small for conventional science model. All right, so that's it. Gonna stop recording